find this V. Okay, so with node voltage, how do you find this V? Okay, I'll just discuss this with you before we move on with the topic for the day. Okay, so step one is you will apply node voltage, and when you do node voltage, there are only two essential nodes as you realize here. This one, we call this as VA, and this one, which is VB. Okay, so you will, I'm not going to find VA, VB for you, but as you know, you will find what is VA and you'll find what is VB. Okay, you'll write the two node voltage equations at A and B, solve them together, and then you'll find this. Let's call this as Vx. Okay, so here what we're trying to find is, if let's assume some values, right? Let's say this is, for example, VA is, let's say, for instance, 10 volts, or let me assume this is 8, so 20 volts. Okay, let's say that is 20 volts, and let's say this is 4 volts. Okay, as an example, when you solve the node voltage equations, these are, let's say, approximately you get these values. I'm just assuming them, you might get some other value. Okay, so what we're trying to say is, if this is 20 and that is 4, what would be the voltage at this point in the circuit, right? Okay, so with this, what we'll do is we'll find the current. Okay, so if 20 volts is here and 4 volts, obviously the direction of current is like this. Okay, so let's first find I. Okay, I will be equal to 20 minus 4 divided by the total resistance, which is 6 plus 2. Okay, so this will be equal to 16 divided by 8, which will be equal to 2 amps. Okay. All right. So if this is 2 amps, right, the voltage across the 6 ohm resistor, V6 ohms, okay, the voltage across the 6 ohm resistor, V6, will be equal to okay, this will be equal to I times 6, right? That will be equal to 12 volts. 2 times 6 ohms, that will be equal to 12. Okay? All right? So, let me put it like this. Right? So, the difference between these two, as you know, the difference between this point and this point here, right, is totally equal to 16 volts. Okay? 16 volts. That's the total difference, delta V. That's what we did. This is your delta V, or VAB, okay, which is nothing but VA minus VB. Because current, we assume current to be flowing like that. Okay. So if this is 12 volts, right, obviously this has to be the other 4 volts. Okay, that's how it will add up to this whole 16. Okay, so if you think about it like that, then what would be the voltage at this point, which is Vx? Okay, Vx will be 20 minus 12, which is 16. I'm sorry, 20 minus 12, which is 8 volts here. So if this is 8, then the difference between those two will be 12. Okay, and the rest is here. So when you add these two, it still amounts to 16 volts. The idea here is, if you have two resistances like this, okay, and you know the total voltage across them, which is, let's say, VAB, whatever it is, right? And this is your V1, this is your V2, right? We know VAB should be equal to V1 plus V2. Okay. If you know one, you can subtract the other to find, or you can simply do I up to find any one of them. This will be I times R1, this will be I times R2. Okay. All right. So a midpoint resistance you can easily find out like this, or you can do one more thing. Okay, let me show you another technique, which if you feel that is more easier for you to do, you can try that. Okay. Actually, that will be the same thing, but let me just quickly show you here. Okay, you can assume this to be V1, you can assume this to be V6. You can assume to be V2, and this will be V12. Okay, and you can write a KVL. Okay, but you'll need to know the currents. So unnecessarily, that makes it much longer. This is a simple way. Okay, we know delta V, which is this minus this divided by resistance, you get the current. So the drop across this has to be 6 volts, right? I'm sorry, the drop across this has to be 12 volts. If this has to be 12 volts, what should be the voltage here? Because you're dropping 12 volts across the 6 ohm resistor. So if this is 20, right, we know that V 6 ohms, right, is equal to the difference between these two, right? VA minus Vx, right? That is the drop across the 6 ohm resistor, okay? This is equal to 12 volts, okay? And VA is 20 volts minus Vx. So Vx will be equal to, okay? So your 12 volts is, this is how you get to 12 volts. Okay, this is a simple way of doing it. Okay, if you want, you can even try the KVL. All right? Do you want me to go over that again?
So about the current, so we get the total voltage between point A and B, and then we divide by the total resistance.
Okay, let me put it to you a little more so. Okay. I just assumed those two values, but you would have got the two values for VA and VB from your node voltage, right? So let's try this one.
So we're just trying to find the current between the two resistors.
Yeah, we are asked to find this point, the voltage at this point. This point is V. Okay. What is the voltage of this point with respect to? So if you assume this to be V, right? So if you assume this to be, let's say V, the voltage across the 6 ohm resistor, right? Voltage across the 6 ohm is the difference of these two, right? The voltage across any resistor or any element, okay, is the difference between its two ends, right? So in our case, okay, this is nothing but VA, okay, minus this voltage V, whatever it is, okay, which we are trying to find, okay. Now, VA we know because we got this from node voltage. This is from node voltage you found out, okay. What we don't know is what is V6 ohms, okay. We don't know this. So if I find this, I can simply rearrange the terms and I can simply say V will be equal to VA minus the drop across the 6 ohm resistor. Okay. All right. So what we'll do here is, so let's assume this is VA, this point is V, and this is your 6 ohms. Right? Okay. So if you look here, this is a series connection. So the total, or let's say the total current I flowing through both of them will be equal to VA minus VB divided by R total. Okay? Which is nothing but 20 minus 4 divided by 6 plus 2. Okay? That will be equal to 16 over 8, which is equal to 2 amps. Okay? So if I is 2 amps, V6 ohms by Ohm's law will be equal to I times R, right? Which will be equal to 2 times R is 6. So that will be equal to 12 volts. Okay, so we know VA is equals to 20 minus 12. Okay, I'll be equal to 8 volts.
Can we use a voltage divider to get the voltage at 6 ohm resistor, like the total voltage between VB?
Yes, for voltage divider, if you do that, you'll have to assume this to be 0 here. So for example, the total voltage, okay, so let's assume this here. Let's say these are the two voltages, right? And this is the voltage you're trying to find, V. This is your 6 ohms, this is your 12 ohms, okay? What is the total voltage across both of these? The total voltage across these is, this is 20 and this is 4 volts, so this will be 16 volts, okay? So if this is 16 volts, you can find the voltage across 2 ohms or the voltage across 6 ohms, okay? So let's find the voltage across 6 ohms. Okay, total voltage times the individual resistance divided by the total resistance, right? So this will be 12. Okay, so that means if this has got to be 12, right? So what will be the voltage here? 20, this will be 20 minus 12. Okay?
And this way it works.
Yeah, any method. So any method is fine, so long as you understand the concept. There are different ways you can solve it by KVL. If you like doing voltage division, that's even better. That's a simplest way of doing it. But the idea here is simply to find a midpoint voltage between two resistors.
Thank you.
No problem. Okay, all right. So let's move on with node voltage. But today what we'll do is we'll include a different type of a source, right? We did everything with independent sources. So let's move to a question where we try to do node voltage with dependent sources. Okay, node voltage. Okay, so the idea here is, let's say I have a voltage source like this. In addition to a voltage source, what we'll do is we'll also include a few dependent sources. For example, here, I can go here, have one more resistance, and I have a dependent current source. Okay, and then I can go here, and I can have a dependent voltage source. Okay. So everything remains the same. The only thing that we change is we want to get this very first step is, okay, represent the dependent source. Okay, in terms of a known value or parameter. Okay, known value or a known parameter. So we want to remove the dependency or represent it in terms of something more reliable that we can incorporate in our node voltage expression. Okay, all the rules will remain the same. If you have a dependent current source that is sending current into the node, then we'll write it as negative. If the dependent source has current leaving the node, then we'll write it as positive, right? So for example, since this current enters this node, when you write the node voltage equation, this will be negative, right? Leaving currents are always positive, entering currents are always negative. Okay. So let's try to understand this because you guys already know how to write a node voltage expression. We'll simply include a dependent source within the circuit and we'll try to solve this. Okay. So let's take this very simple question where we have one dependent voltage source. Okay, and then we'll have more than one source so that we look at all different cases. Okay. So here, to start with, on one side there is no dependent source, so you guys know how to go ahead and write the equation for one of the nodes. Okay, so here there is no dependent source on this side. Okay, so 2, 5, 20. Okay, so this is 2, this is 5, and this is 20 volts. And 10, 2. Okay, and this is 8 I naught. Okay, where I naught is equals to this current. Okay, so what are we asked to find? Find the power dissipated in the 5 ohm resistor. Okay, so we need to find power of the 5 ohm resistor. Okay? We know how to do power, V times I squared R. However you like to find that out, it's perfectly fine. Okay? All right. So by node voltage, what we'll do is we'll mark the essential nodes here, right? The first essential node being this, which we'll call this as VA. Okay? Here, this will be VB. Okay? All right. VA, VB. Let's mark a common ground, so we reference all our voltages. This would be 0 volts. Okay, this is how we'll reference. Okay. Now, this dependent source is a voltage dependent source because you see a polarity there, right? Plus, minus. So we'll call this as VD, which is our dependent source. Okay, VD is our dependent source. Okay. So, as you know, VD is equal to 8 I naught. Okay. Now, what we want to do is we don't want to keep I naught in our expressions. Since we are doing node voltage, what we want to do is represent the dependent source okay, in terms of the node voltages. Okay. Why do we need to do that? Because we have two unknowns, right? We have two unknowns. We have VA, we have VB. So to solve for VA, VB, we need two equations, VA and VB. Okay? So two unknowns, we need two equations. Right? But if I include I naught as one more unknown, then I'll need three equations. Okay, we don't have three equations. We have one equation here and one equation here. So what we'll do is we'll try to write I naught in terms of these two so that we can solve it with two equations and not three. Okay? Because if we keep I naught is also an unknown, we don't know what the current is, we only know I naught if we know these two voltages, right? So what we'll try to do is we'll get rid of I naught and represent I naught in terms of the node voltages. So when we solve them, we'll also find I naught. Okay? So this is always the first step whenever you see a dependent source. Okay? Alright, so as you can see from here, I naught flows from VA to VB, right? So I naught will be equal to VAB, okay, the voltage across A and B, right, divided by the resistance, which is nothing but 5 ohms. Okay, so I can write VAB, as you know, VAB is nothing but VA minus VB. So what we did is we represented the dependency in terms of the node voltages. Okay, so from here we can say VD, which was equal to 8 times I naught, is nothing but 8 times VA minus VB divided by 5. Okay, so that will be equal to 8 over 5 VA minus VB. Okay, so that is our VD. Now let's carry on with our regular node voltage equations and let's write the node voltage expressions. Okay, so let's do step 1, which is node voltage at A. Okay, so when I do node voltage at A, okay, nothing changes, everything is as always what we do normally. So when we do A, 1, 2, 3, okay, so VA minus 20 over 2 plus VA minus 0 over 20, okay, plus VA minus VB over 5 is equals to 0. Okay. So to get rid of the highest denominator, I'm just going to multiply this whole thing by 20. Okay. That way we can rationalize, come up with a expression or an equation that does not have a denominator. So here you'll have 10 VA minus 20, right? 10 times, and then plus VA plus 4 times VA minus VB. So equals to 0. Okay. So 10, 4, 14, and 1, 15, right? So this will be equal to 15 VA, right, minus 4 VB, okay, equal to 200. Okay. All right. So let's do node voltage at B. Okay. So when we do B, you again have 3 branches, 1, 2, and 3. Okay. So let's go here and we'll say node voltage at B. Okay. So when we do node voltage at B, everything is subtracted from the node B, right, or VB. So we'll go here and say VB minus VA over 5 plus VB minus 0, which is in this case over 10, plus what will be right here for this branch?
VB minus VD
Exactly, VB minus VD.
over 2.
Perfect. Okay, and then we'll substitute VB. Okay, exactly as a voltage source, just as we did here, VB minus 20. Instead of that, we'll just write it VB minus VD. Okay. All right. So we have one choice. Either we can substitute VD now, or we can substitute later. Let's make things simpler. And what we'll do is let's just get rid of this denominator. When it comes to multiplying one more time, we can do it once again. Okay, I'll just leave it like that. Okay, so here, what do I have? I have VB 2 times VB minus VA plus VB, right? And then this will be plus 5 times VB minus VD is equals to 0. Okay, so let's put A and B terms together so that we can write this equation in a cleaner format. So if you look at the number of VB terms, 2 VB and 1 is 3 and 5, 8. So that's going to be equal to 8 VB. Okay. Minus 2 VA. Okay, and then you have negative 5 VD. Okay. So as I mentioned to you, we have only 2 equations, so we cannot have a third unknown there. Okay, we want to get rid of VD so that we can only solve for A and B. Okay, so what we'll do is we'll use this expression, okay, and we'll substitute this expression that we got here for VD. So this was VD, so VD should be this. Okay, where VD is equals to 8 over 5 VA minus VB. Okay, we want to get a equation only in terms of VA and VB. So this will be 8 VB minus 2 VA, 5 times, okay, we'll substitute this. So that substituted value will be 8 over 5 VA minus VB. Right, that was the value for VD. Okay. Okay, so this will cancel 5 and 5, so you'll have negative 8. Okay, so this will be 8 VB minus 2 VA minus 8 times VA minus VB. Okay, so minus of minus will be plus, so that will be plus 8 VB and 8 VB, 16 VB. Okay, negative 2 VA and negative 8 VA, that will be negative 2 VA. Okay. You can take 2 common and rearrange the terms, that will be equal to 5 VA minus 8 VB is equal to 0. If you take negative 2 common or divide by negative 2, that's what you do. Okay, so if we solve equation 1 and 2, you'll get VA and VB. So just multiply this by 3 and subtract it from there, you'll get rid of VA. So that should give you, if you guys double check, VB should be 10. From what I see, if you multiply that, VB should be. Okay, can you check that? So multiply this by 3 and subtract it from equation 1. So 15 will cancel, 8 3 times is 24, so plus 24 minus 3 will be 20, 20 VB equal to 200, so VB will be equal to 10. Okay, let me do it here. Right, so you can cancel these. Okay, substitute VB equal to 10 here, and you'll get VA equal to 16. All right, so what is the power of the 5 ohm resistor? Okay, it depends how you want to calculate that. If you simply want to calculate it like without knowing I naught, then you can do it in one possible easy way. The voltage power of 5, right, will be equal to, okay, V square divided by R. Okay, so V square divided by R means VAB square divided by the resistance. Okay, V square by R. Okay, power across, you can write it in any one of these forms, right? VI or I square R or V square over R. Okay. In these cases, here you need to know both V and I. Here you need to calculate I naught, which is the current. Okay, or you can do this. Okay, let's try this one. Okay, which is simpler. So this is nothing but VA minus VB, because VAB is VA minus VB divided by R. Okay. Obviously, because it's a resistor always absorbs power, we'll put a plus sign. Okay. We know A and B values, so in our case, A is 16 and B is 10, right? So 16 minus 10 squared divided by R, which is 5. Okay, so 6 squared divided by 5. Okay, 36 divided by 5, which is 7 is 35. So this will be 7.5 volts. I'm sorry. Not 5 is 7.2, not 5. 2 times 8. Okay, this is a very interesting problem. If you do this, if you set up the equations properly, then you're good. You understand node voltage very well. Okay, so I'll let you set up the equations. Do the exact same thing that we did here in terms of representing the dependency, and tell me what you get. Okay, so this is a good problem. Let's try this, and then we'll look at another one. Okay. So here you have a current source, okay, which is 3 amps. Okay, followed by a parallel resistance, which is 200 ohms. Okay, and then you have a 10 ohm resistor. Okay, and this is I naught. Okay, so 5 I naught and that is I naught. Okay, you need to find what is V naught. V naught is this voltage. Okay. You need only one equation to solve this because there is only a single essential node. There are no two essential nodes in this case. Okay, there's only one essential node, and if you write one equation, that should be enough to solve it. Okay, so first look at the source, set up the equation, and then we'll solve it. Okay, so here we'll assume one ground, okay, as always. Okay, if you look at nodes where you have 3 or more elements connecting, that would be this, and this would be this, right? Okay, those are the two nodes where you have 3 or more elements actually joining or connecting together. So technically, those are possible candidates for essential node. Okay, since nothing is connected between these two, they are essentially the same. Okay, because there is nothing connected between those two nodes, they are essentially the same node. Okay, you can write this as VA, VX, VB, or anything that you want. Okay, let's say we call it as VA. All right, if I call this as VA, that means this is the voltage across this. Okay, since this is in parallel with this would also be VA and this would also be VA. So you can write it as VA, but a better option to write this would be V naught because they are exactly the same voltage with respect to ground because you're measuring that here. Okay. If you solve for VA, at the end you can say V naught is equals to VA, or you can still set it up as V naught and solve everything. That way you don't have to do one extra step. Okay? Understand that this is the voltage across a parallel element, and therefore it will be the same voltage. Okay? If you solve it as VA, at the end you can say VA is equals to this. Or you can simply write the equation in terms of V naught. Okay? Why? Because they are parallel. Okay? They are parallel, and hence they'll have the same voltage. If you measure the voltage here, and then you measure the voltage across these two, and this, it'll always be the same, because they are parallel elements. Okay? So the very first thing we want to do is to represent the dependent source, right? So in this case, our dependent source is the following, right? This is our dependent source. It's a voltage source because we see a polarity, we say this is VD. Okay? VD is equals to 5 times I naught. Okay? And we need to represent I naught. Okay? I naught, as you can see, I naught flows from VA to the source, right? Generally, when you have a resistance and you have VA and this is VB, let's say that my resistance is 20 and this would be I naught, I would simply say I naught is equals to VA minus VB over 20. Except in this case, the voltage at this point is known to us, right? So the voltage at this point, because it's connected to 80, the voltage at this point is 80 volts because it's directly connected here. Okay, it is that voltage. Okay, the same voltage. I don't want to draw it as a current direction, so I'll just say like this. Okay, there is nothing connected here. If there was an element or a resistor connected here, this will not be 80. Okay, measuring here is as good as measuring here because there is nothing connected in between them. Okay, it's a direct connection. Okay, so what I can do is I can go here and I can write I naught as a current that goes from A to the 80 volt source through a 20 ohm resistor. Okay, flows from VA to the 80 volt source, okay, through a 20 ohm resistor. Okay, so VD will be equal to 5 times, we'll just substitute I naught there, minus 80 over 20. Okay, so that will be equal to VA minus 80 over 4. Okay, we'll leave it as this. Okay, now if you write the node voltage equation at VA, there are 4 branches connected to VA, 1, 2, 3, 4. Okay, so I want you to write the node voltage equation at VA and then we'll solve it. Okay, there is only one equation and one unknown, which is VA. Okay, when I do node voltage at A, 3 amps is flowing into the node, so we'll write this as negative 3. Okay, plus here you have VA, this is 0. So VA minus 0 divided by 200. Sorry. Okay, how do I write this?
V naught minus VD.
Okay. So here's the thing, right? So let me draw this branch here for 1 second, and then you guys can reason this out with me, where you have, and what you said is true, you have a voltage source like this, and like this, right? So minus plus, let's say VB, and this is 10 ohms, okay? As opposed to that, just so that we understand the difference between the two,
Does it change the negative to positive then?
yeah. So in this case, right, here, if you think about the current flowing down, right, this will be VA minus VD over 10, right? This is VD and this is VA. So the difference of the voltage will be VA minus VD, okay? But if you're doing the same thing here, this will be VA minus of minus VD. Okay, because you have the negative sign facing. Okay, so this is as good as saying, because the positive sign is facing here, plus VD. Okay, we just generally don't write it as plus VD because plus is, nothing is there, it's understood to be positive. Whatever terminal is facing this VA, we write it like this, so VA minus VD, here it's negative, so we'll write it minus of minus. Okay, so please understand the difference. When you have a reverse source like that, then we'll write the polarity of the source. So in this case, this is going to be equal to VA minus of minus VD divided by 10. Okay, which is the third branch. The final branch, as you know, because you have plus 80 facing the VA node, VA minus 80 over 20 ohms. Okay, so let's multiply this whole thing by 200. Okay, so that will give me negative 600. Okay, and we cancel 200 and 200, so that will be VA. 20 times VA plus VD, and then plus VA minus 80. Okay, so if you put together all the VA terms, you have 20 and 121 and another 122 VA.
Yeah, isn't that like 200 divided by? My bad, it should be 10.
Yeah, so it'd be, yeah, it should be 10.
This is 10, right?
It should be 10 times VA minus 80,
10 times.
because it's 20.
Yes, you're right. You're right. Correct. Okay, 10 times that, right? So we have 31 VA in that case, correct, you're right. So that will be equal to 31 VA plus 20 VD. Okay, and I have 800 there, negative 800 and negative 600, so that will be negative 1400. Okay, so let's put back VD here and see what we get. So we need to substitute this value for VD. VD is this. Okay, so that's going to be equal to 13.1 VA plus 20 times VA minus 80 over 4 plus 14 minus 14. So that will be 5 times, right? So 5 and 31 will be 36 VA. Okay, and 580 times will be negative 400. Thirty-six 5 times, I assume, is 180, so this will be for 50 volts. So V naught equal to VA is equals to 50 volts. All right. Okay, so with this approach, let's take, here you had a single node, one equation, you could solve everything. Okay, let's take a slightly more involved question where we have two of these dependent sources, and we try to resolve that to get a answer. Okay, by the way, let me just put together, here's a good question, I would like you guys to think about it. If you face any difficulties, remind me. I'll solve it, but just try this. Okay, I'll just leave this here for you to try. But one thing, this question does not have a dependent source, but it's a good question. That's why I want you to just give it a shot. Need to find the branch currents I1, I2, and I3. Okay, I'll put them in red, so need to find what is I1. Okay, just try this out. If not, I'll solve. Okay, let me just give you one hint here. Okay, if you look at all the essential nodes, right? So let's say this is one essential node. We'll call this as VA. Okay, here is one more essential node. This is VB. Okay, and the third essential node is here, VC. Okay, because VC is directly connected to the source, VC is already 80 volts, so you don't need to. We know the voltage here. Okay, so you only have two unknown nodes, A and B. If you find A and B, the whole circuit is solved. Those are the only two unknowns. VC is already known because it's directly connected here. Okay, there's no element in between, so you only have to write two equations. Okay, VA and VB. Okay, if there was an element here, for example, if there was a resistor here, then VC will not be equal to 80. Since there's nothing at that point, if you measure the voltage at C, it will give you exactly 80 volts, which is the source voltage. Okay, let's try this, which is a double dependent source problem. Here you have This is I naught. Okay, we need to find the following, V1, V2, V3.
Is that 11.5 right now?
11.5. So this case, I think we'll end up with 3 equations. We'll see if we can somehow reduce that to 2, because otherwise it's going to be a little tricky to solve out. We'll find out. Okay, as always, let's go with ground. I'm going to highlight the essential nodes, 1, 2, 3. And they all correspond to V1, V2, V3. You can write them as V1, V2, V3, or you can set them up as VA, VB, VC, where V1 equals to VA, VB is equals to V2, and V3 is equals to VC. So we'll somehow need to get rid of one of the expressions, but anyways, we'll try. Okay. So let's go with getting rid of this dependent source VD, which is 11.5 times. So I naught flows from VB to the ground, right? So I naught will go here and say I naught is equals to VB minus 0 over 4. Okay, and since VD is equals to 11.5 I naught, this will be equal to 11.5 VB divided by 5. Okay, I'll just multiply and divide by 10 to make it more reasonable. That way I get rid of the decimal. Yes, we'll come up with 3 equations. We'll see how to reduce them. Yeah, it's 11.5. Okay, so let's go with node voltage at A. Okay. When we do node voltage at A, you have the incoming current minus 5 I naught. Okay, and then you have, okay, so this is also a dependent source, right? So this is ID. Forgot to label this. This is ID. Okay, just as you have VD, there is also ID. So in our case, ID, which is equals to 5 times I naught, will be equal to 5 times I naught is VB over 40. So that is nothing but VB over 8. Okay, so we have one more dependent source. Okay, and here you know this will be equal to VA minus 0 over 20, and then we'll go here, VA minus VB over 5 is equals to 0. Alright, so I'm just going to replace this by our value of I naught. This is nothing but minus 5 VB divided by 8 plus VA over 20 plus VA minus VB over 5 is equals to 0. Okay. So I think it would be best if we multiply this by 160, or 40 is good, right? If you multiply this whole thing by 40, that should be fine. Okay, so that would be 5 times. Okay, so that will be equal to 25 VB Okay, this will be 2 times 2 VA. Okay, and over here you'll have 8 times. So 8 times VA minus VB. Okay. All right. So if we put together all the VA terms, 10 VA. Okay, 25 and 8, that will be 33. Yep. Incoming. Okay, so that's good. At least we can use this relation whenever we need to get rid of one or the other. Okay. So that will really help us eliminate one of the parameters, either VA or VB. Otherwise, we'll have to solve 3 equations. This is really helpful in terms of solving our equations. Okay. Okay. Let's do node voltage at V. So if you do node voltage at V, okay, V is VB minus VA over 5 plus VB minus 0 over 40 plus VB minus VC over 10. Okay, so we'll simply multiply this whole thing by 40 to rationalize this. Okay. So 8 times, okay, plus VB plus 4 times okay, so you'll have negative 8 VA. VB is, this is 9 and 13 VB. Okay, minus 4 VC is equal to 0. All right. So let's take the last one, which is node voltage. Okay. Okay, so VC minus VB over 10. Okay. Here you have the positive terminal facing, so we'll have VC minus VD over 5. Okay, plus VC minus 96 divided by 4. Okay. So we'll multiply this by 20 so that we can easily get rid of things here. So if I do that, it will be 2 times plus 4 times VC minus VD plus 5 times VC minus 96 is equal to 0. Okay, so as you can see, there is no VA yet, right? We don't have VA in this equation. So let's accumulate VB terms. There is only one VB, so minus 2 VB. Okay, how about VC? 2 and 4, 6 and 5, 11. So plus 11 VC. Okay, minus 4 VD. Okay, will be 96 times 5. So 100 times 5 is 500 minus 20. So that'll be 480. Okay, so all we need to do is, we'll need to rewrite VD. Okay, let's rewrite VD. All right, so that will be equal to minus VB plus 11 VC minus 4 times VB by 400. Okay, so I can cancel this 100 times, right? That will be 100 times. Okay, so this will be equal to okay. All right, so I'm just going to multiply this by 100, so I can get rid of everything. Okay. So that will be equal to minus 200 VB plus 1100 VC, okay, minus 11.5 VG. Okay. So VB, we can put that together, and this will be equal to 315 VB plus okay, so one way to solve this, as I mentioned to you, is using a matrix approach, or the lengthy way would be to, give me 1 second, let me set this up and then I'll show you. Okay, so A, B, and there is no C. So A is 10, B is minus 33, and there is no C. So we'll write 0 for that. Here, negative 8, 13, and minus 4. So negative 8, 13, and minus 4. Okay. There is no A here, so we'll write a 0 for it. 1100 and, sorry, 315 and 11. Okay, will be equal to first 0, 0, 0, 0, and 48. Okay, so I'll show you another way to solve this. Okay, so let's keep this equation. We'll use this. Okay, all right. Since it's only in terms of B and C, what I want to do is convert this expression in terms of B and C, so we can use those two to solve. So I want to get rid of A. So how do I get rid of A? So VA from here is nothing but 33 VB by 10. Right? 33 VB by 10. So what I'll do is I'm going to substitute this here so I can get rid of A from this equation. Okay? So I'll write this as negative 8 times 33 over 10 VB. Okay, which is this, right? Plus 13 VB. Minus 4 VC is equals to 0. Okay. So just to get rid of this 10, let's multiply this whole thing by 10, so I can get rid of that 10 from there. Okay. So now what I'll have is negative 8 times 33 VB plus 130 VB minus 4 VC is equals to 0. So 24, 3, 8 times is 24, 24 times 11, so okay, plus VB minus 4 VC is equals to 0. Okay, so from here, what we'll do is, if you subtract this, you'll have negative 134 VB minus 4 VC is equals to 0. You can substitute this in here and you'll find VB and VC.
Will not be 40 VC?
40 VC?
Into 10.
Yep. You're right. Thank you. That should be 40 VC.
How'd you get VA again? How'd you find VA?
This one?
Yeah.
So if VA is equals to this, right? So 10 VA minus 33 VB is equals to 0. Okay? So 10 VA, we'll move this to the other side. So that will be equal to 33 VB. Okay? So VA, if you divide both sides by 10, okay, you move to the other side. Okay. All right, so once you substitute that, you can solve. You can solve it any way. What you could do is you can substitute VC is equals to 134 divided by 40 and substitute that there, and then you can do that, or any other way you choose to. Okay, you can multiply it by something. Okay, so solve for those values. I'll see if I can find the answer and share that with you. But let's stop here, and once you find those values, A, B, and C, keep in mind V1 is equals to VA, V2 is equals to VB, and V3 is equals to